Hey guys, some of you guys were wondering how to enter equations in Word, and the way you do it is if you follow the control panels at the top, if you follow all the way through Insert, and you go all the way to the end, you find the equations, click down the drop menu. Some of them are already included there, so the area of a circle, Pythagoras' theorem. But if you go to Insert a new equation, a new tab comes up, and these are different variables or functions that you can include in your equation. So if you want something that involves just basic math with the multiplication, division, subtraction, and the sum with an equal sign, you can use these variables. You got some Greek letters that you might be needing: theta, popular for angles. You got pi, you got mu, and you got phi as well. If you need more Greek letters, you can actually go and look for the Greek letters. They come in lowercase and uppercase. You can also include different operators, which you might need to show relationships, whether values are equal or different values, or proportionate or not proportionate to each other. You also have arrows if you want to add some arrows into your equations, and then you got other geometric relationships here. But we're going to be just using basic math. So what we'll do is the equation. We'll do both. The equation for an open end pipe and a closed end pipe, both without the end corrections and with the end corrections. Let's have a look at this. All right. So the first one is the open end pipe. Also, with this particular variable, you can add subscript. So that's important where you want to differentiate between a variable that occurred initially, or a variable that controlled later, that happened later, or a particular frequency value. So for us, that's going to come in handy because we are going to have the general expression of the wave produced by a pipe of a particular length of frequency n, where the frequency can be anything. For an open pipe, it can be any number, any whole number. Okay, so the equation is frequency n, so I'm just using my keyboard here, of a pipe is equal to, I've got a division sign, I've got a division function here. I can present it in different forms. This one's probably the most appropriate. The frequency number, the speed of sound in air, to L, that's a capital L, and that's the general expression for an open pipe. Now we can copy, and rather than me type that up again, I can include the condition for a closed pipe. So it's the same thing, except I have a factor added, and that particular factor is and that L can actually change that around, so that no longer that length is increased by a factor of E in both ends. So we can actually even insert a bracket to make this look very nice. We've got a couple of bracket options. We go that one, and we go the length of the pipe plus 2 times the necessary end corrections on both sides of the open pipe. Okay, so let's have a look at the closed pipe now. Okay, so we'll go insert an equation, follow it through, Again, we're going to use a symbol. Frequency at a particular harmonic is equal to that particular harmonic multiplied by the speed of sound in air times 4 of the length of the pipe. Okay, and when we consider the end correction of this expression, that changes the length by one side. So that means we only consider the end correction on one side. So it's only length plus the end correction required of the open side of the closed pipe. Okay, and just a reminder here, it's an equation, n is equal to the odd number, so that is 1, the harmonic at 1, the harmonic at 2, the harmonic at 3, the harmonic at 5, the harmonic at 7, and etc. Whereas for this one, the harmonic is just integer values, so they go up from 1 to infinity. 1, 2, harmonic at 3, harmonic at 4, and so on.